Hey, what's up everyone? Jason Turley here. Once again, back with more Pico CTF challenges, everyone's favorite beginner-friendly capture the flag website. In the last episode, we checked out 5 challenges from the general skills category of Pico CTF 2024 that wrapped up recently. And now we're just going to continue on with the next challenge in the series of binhexa, which is a combination of 2 words, binary, which is ones and zeros, and then hexadecimal, which is a combination of numbers and letters, numbers 0 through 9, and then letters A through F. So if you ever do any type of disassembling or debugging and you see memory addresses, they're always written in hexadecimal format. So without any further ado, let's get started. Let's read the description. How well can you perform basic binary operations? And then it gives us an instance to launch. So let's click there. Sweet. So it gives us a netcat connection line with a host name and a port to connect to. So let's copy this. Open up a terminal. Make sure it's nice and big so we can read it. And then slam in our netcat connection line. And we get this message, we get this banner. Welcome to Binary Challenge. Your task is to perform the unique operations in the given order and find the final result in hexadecimal that yields the flag. So we're given 2 binary numbers, binary number 1 and binary number 2, that are 8 bits each. And then we see question 1 out of 6, operation plus. So perform the operation on binary number 1 and 2, and then we need to enter some type of result. So what is it asking us to doing? Binary operator plus, or binary and, if you will. So to understand some of these binary operations, let's break out the whiteboard and let's make a very basic truth table, just like that. We'll have input number 1, input number 2, and then we have the output. And this is for binary operation and, which can be symbolized with a plus sign or an ampersand. And a binary is either on or off, either true or false. So these are the options, right? Either 0 or 1. So let me write these out here. And now just going from the top, we'll start right here. Can something, if the 2 values are 0, then the output will be 0 because both input values are off, both things are false. So it makes sense that the output is 0. Now here's where it gets a little tricky if you've never encountered this before. We have 2 values, 0 and 1. Can something both be off and on at the same time? No, it can't. It's either off or it's on. Or can something be true and false at the same time? No, it can't. Same thing for these values right here, this third line. It's still something that's on and something that's off. So the output will be off. And then finally, if we have 2 things that are both on, then the result will also be on or a 1. So can we have 2 things that are true at the same time? Yes, but can something both be true and false? No. So how this comes into play into binary addition, if we look at our binary numbers, I forget what they were, but it was something along the lines of like 0, 1, 0, 1. And we try to add that, for example, with this. Do our addition. So 1 and 1 is 1, 0 and 0 is 0, 1 and 1 again is on, and then 0 and 1 is 0. So this right here would be the result. So how can we translate that to our challenge here, our capture the flag challenge? So instead of trying to manually do this and write it out by hand, we don't need to do that. We can use a programming language like Python. So I'm going to open up a Python shell now, and I'm just going to create some variables to keep track of our first binary. Now, if I just slam it in here like this with the 0 and the 1s and hit enter, it is going to give me an error because it thinks this is a decimal, and decimals cannot start with the number 0. It doesn't make sense. If I try it with the other one, binary 2, and slam that in, it will work. But then when I go to print it out, binary 2, that's fine. If I try to print out the type, binary 2, it gives me integer. So that is incorrect. We don't want that to be an integer. We want it to be notated as a binary value. So how can we do that? Once again, creating my variable binary 1. And then instead of just slamming in the binary number like this, we need to prefix it with 0b. If we wanted this to be hex, we would do 0x. But since we want this to be binary, we prepend a 0b in front of it. And now if I do binary 1, or the type binary 1, still gives me class integer. Why are you doing that, Python? That's fine. Let's roll with it. Let's create our second binary, binary 2, OB, and then slam this in. And now we need to add these together. So binary 1 plus binary 2. And we get an integer as the result, but the prompt is expecting us to enter it as a binary value. And we can simply do the binary of 346. And we get our value. Alternatively, we could have just wrapped this whole addition statement inside the bin function, and it will give us the exact same result. We don't want the OB when we enter our answer because it's not expecting it in that Python format. So take out the 0b and just give it the 8 bits. Smash the enter key. Let's see, did our challenge server die? No, it's still up and running. That should work. Yeah, not sure why it's hanging like that. PS, EF, grep, netcat. Did that kill it? Okay. For whatever reason, our challenge server died. Maybe it timed out because we were taking too long when I was showing how to do it in the whiteboard. Let's rerun this. Okay. Back to our Python interpreter. Binary 1 equals 0b. So same exact steps. And same thing for binary 2. Now let's do the addition. Now I can just tab complete. Nice. So grab this, chuck it in there, hit enter, and we get correct. Next, it asks us to perform the OR operator, and I'll go just a little bit quicker, just so the netcat connection doesn't time out. So how can I erase this? There we go. Okay, that's erased. Same thing for OR. It's represented with a vertical pipe or just the word OR. So if I have our truth table here, we have the first value, we have the second value, and then we have some type of output. It can be 0, 0, 0, 1, 1, 0, which is the same thing, or 1 and 1. So can something be true or false, or off or off? No, so output would be 0. Can something either be on or off? Yes, it can. Can something be either true or false? Yes, it can. So the result will be 1 or on or true, however you like to call it. Same thing for this third value. And then can something be true or on? Yes. So if you look here, I know this is pretty sloppy, but it's pretty much the inverse of our AND statement, where or there's only one way to get a 0 with an OR when both values are off. Or there's only one way to get 0 with an OR statement when both values are off, both values are 0. And every other interpretation will always give you a 1. When we had our AND statement up before, the only way to get a 1 was down here when both values were on. and everything else was a 0. It's a neat little computer programming trick. Let's see if we can represent this another way. Binary truth tables. Let's pull up a good example. Here we go. This is good enough. So we see we made a very similar table for our and we see on over here on the end is our or. Exact same thing from what I drew over here. It's just a lot prettier. So the only way to get a value of 1 for an AND gate or an AND statement are when both values are 1, and then the only way to get a 0 for an OR statement are when both values are 0 or when both values are off. So now let's go back to our Kali Linux terminal, and hopefully nothing timed out. So since we have these variables here, we can quickly just do binary of our 2 binaries that we created, and we want an OR statement this time. And we get all 1s, everything is turned on. So let's slam that in there, and awesome, we move on. Okay, the next question is very similar. In fact, it might be the exact same as the first one. It wants us to do a binary and. So let's see if that's any different than the plus that we did earlier. And it is. We see that it chopped off some of the values, right? These first 2 numbers, 1 and 0 is 0. So that's why there's nothing there. So we come over here, we slam in our result, we smash the enter key, and now it wants us to do the same thing for multiplication. So very similarly, just come over here, change our statement to multiplication, and we get this long number that we can just copy, paste, and slam it in. Sweet. So we're almost done. Now we need to do a left shift. So shifting all the values over by 1 that we see here. We're shifting everything over by 1 bit. Very easy to do in Python. Okay, we get the result in decimal. I keep forgetting. There we go. Convert it to binary. Grab it, slam it in. And we have one more. This time it wants us to perform a right shift. So binary 1, right shift over. No, it wants us to do it on binary 2. Shift over to the right by 1 byte. Keep doing that. Jeez. Convert that to binary, grab it, and slam it in. That was correct. And the final thing, enter the results of the last operation in hexadecimal. So can I simply do hex of this? Let's see if Python likes that. OX37. Sweet. And we get our flag. Let me make this nice and big so everyone can see it. Pico CTF, bitwise operation successful. So I did all that in Python, just using the Python interpreter. We could have also alternatively used a tool like Cybersecurity, which is a great online capture the flag resource. And we could have probably performed much of the binary operations in here. So if I just type in binary, we see to binary or from binary or and. We could do logical ands. Set the format to binary, but I like using Python when I can. I think it's always a great tool to have, and it's installed by default on Linux. Let's check out this binary search challenge. The description reads, want to play a game? As you use more of the shell, you might be interested in how they work. Binary search is a classic algorithm used to quickly find an item in a sorted list. Can you find the flag? You have 1,000 possibilities and only 10 guesses. Cybersecurity often has a huge amount of data to look through, from logs, vulnerability reports, and forensics. And that's very true, right? If we're looking at like a cybersecurity analyst or any type of cybersecurity defender who needs to look through all these logs, all this data, local logging and remote logging from legitimate users, just accessing the system resources, accessing other resources, and then like bad threat actors who might be inside the network who have breached the system. That's a lot of data to parse through. So having some type of algorithm to scan and parse and sort through it and save time really becomes incremental and key. So they're really kind of harping on getting into that habit of doing algorithmic thinking in this challenge. So practicing the fundamentals manually might help you in the future when you have to write your own tools. And then it gives us a challenge.zip file. So let's copy that link, come over to our terminal, go into our YouTube Pico CTF directory. What was this challenge? Binary search. Now cd into it. Download the zip file. Oops, added a little tilde at the end. Get rid of that. Unzip challenge.zip. Okay, and we see that it created basically a home folder. Home, CTF player, drop in, and then we see guessinggame.sh. So that seems like it is a shell script. So navigate there. Nice. So if we wanted to, we can open it up, or we can just run it. Okay, I'm thinking of binary number between 1 and 1,000, and then it gives us these traps, and it exits saying it can't open this. So what's going on? Let's open this up. Okay, we see the interpreter. That's what the shebang line is. The exclamation point, or the pound and the exclamation point, bin bash. That is saying it is expecting to be ran in the bash shell, but my current shell is Z shell. If I just do a PS, we see that I'm in Z shell. So if I want to run this command, I have to do bash and then guessing game, or I can just enter the bash prompt itself. And now we see that I am in the bash shell, no longer in Z shell. So now when I give this a run, I don't get that error because the Z shell was not properly interpreting those variables and those values, and it was like throwing a temper tantrum. So I'm thinking of a number between 1 and 1,000, and we get to enter our guess. So this is where thinking like a programmer, thinking algorithmically comes into play. So we only have 10 guesses, we have 10 tries, so I can't just start at 1 and then 2, 3, 4. I can't easily brute force this. What I will need to do is use some type of strategic approach. So if I know the number is between 1 and 1,000, why don't I start right in the middle at 500? And the game is kind of nice. It gives us a hint, right? A tip. It says higher, try again. So now I know the number is higher than 500. It will never be lower than that. So now my search space changes. So now I want to search between 501 and 1,000. So let's enter 1,000. Maybe that's the number. No, it's lower. So now I'm searching between 501 and 9999. So now I want to pick something roughly in the middle of that. I'm going to do 750. Now I need to go lower. So it's everything between 500 and 750. And it is kind of repetitive, but we're just going to continue on. This might not be perfectly in the middle of those two, but let me do 625, even lower than that. What about 550, even lower? 525, lower. What about 510, lower? 505, lower. Oh my goodness, 502, higher. 503. So we exceeded our number of guesses. So it's probably 504. Let's do this again. Once again, entering 500. This time it's lower. 1, higher. 250, so on and so forth. It's lower than that. What about 175? Lower. What about just 75? Higher. 125. Okay. 150. It's lower than that. 135. Higher. 140. Higher. 145. Okay. So I'm not doing the greatest job at solving this challenge. But we do have a thought process. We do have some type of algorithm in our heads that we're following. So let's try to actually convert this to code. So I'm going to open up two screens. Ignore that. Try to make these even. Let's open up our guessing game on one side of the terminal, and now in this other one, let's make something called solver.py. User bin environment variable Python 3. And we can just give it a little comment on what this is. Guessing game solver using binary search. We know our low value is going to be equal to 1, and our high value is going to be equal to 1,000. And now we want to do some type of game loop. So while true, we want to create some type of guess. So we want in the middle of 1 and 1,000. In our case, that will be 500. So what we can do is we can add low and high together and then divide that by 2. I'm doing 2 division symbols. If I just do 1, Python will give me a decimal point or a floating point value. I just want that whole number, that integer. So we're going to do a double division. Now let's print out try guess. Guess. Using a Python formatted string, so add an F in there. Now let's do result equals input. Higher or lower. Let's make whatever that user input is to be lowercase, and you'll see why in a second. So if we need to go, we have 2 options, right? We have if lower, and then we have like if higher. So if we come over here and we try to play the game, enter your guess 500, it tells us to go higher. So there's 2 cases. So if I want to go higher, now my search space isn't between 1 and 1,000. It needs to be between 500 and 1,000. So let's solve that case first. So if h and result. So if it is the case that we need to go higher, the new minimum value is 500 or 501, right? Because we know it will never be less than 500. So we can just discard everything at 500 below, right? 500 to 1, we're never going to guess those numbers because we know it has to be higher than 500. So if it tells us, hey, you need to go higher, then we need to update our low value, and that would be guess plus 1, right? 500 plus 1, or 501 in this case. Otherwise, if we need to go lower, then we just do the opposite, guess minus 1. Else, we'll just do a print 1. So let's see if this works. We can do a little banner statement. Welcome to the guessing game solver. Print. Hit Control C to exit. Open up yet another tab, and now let's run that. Python 3 solver. Let's see if this works. So welcome to the guessing game solver, try 500, and we know we need to go higher, so higher or lower, high. Now it asks us to try 750, so we shove that in there. Higher, okay. Tell the solver that we need to go higher. Try 875. Again, it wants us to go higher. We still haven't gotten the number. 938, it's doing all the math for us. This time we want to go lower. 906. Even lower than that. 890. Lower. 882. Higher. Just type H. 886. Higher again. We're coming up on our limit. There we go. And we got it. Congratulations. You guessed the number correctly. 888. So how many tries did that take? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we just got it. Let's run this one more time. Actually, I'm confident in our program. We don't need to run this. Let's can I exit this? PSEF grep guessing game, grep bash, kill tac9 this. I need to run that as root. There. Okay, now let's just go over to the challenge instance, launch the instance. So we solved it locally on the downloaded zip file, but now we need to actually solve it live against some type of challenge server. And this time, instead of netcat, it gives us an SSH server to connect into. So let's slam that in there. We're logging in as the Pico CTF player. Yes, accept the fingerprint, and now paste in this password. Sweet. So it automatically pops us into the guessing game. We can just run our solver that we wrote. Try 500. Higher, H for higher, 750. Even higher than that, 875. Lower, 812. Lower. So kind of repetitive, not groundbreaking engineering by any stretch of the imagination. A lot of it, or I guess all of it, really is just guessing and trial and error. And we might run out of tries here. 771, lower, 770. Nice. So we did get it. How many tries did that take? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we did, in fact, exhaust all 10 tries. That was our last one. But sometimes it's better to be lucky than good. And that was just enough tries to solve it. So feel free to implement that challenge, implement this binary, this Python script, this binary search guessing game, any other way. This is just how I did it. So it's fine, it got the job done, but it wasn't necessarily fast. It always took us either 8, 9, or 10 tries. We're always getting towards the end there. Moving along, let's wrap up with this challenge worth 200 points called endianess. So know of little or big endian, and then there's a file to download. So if you're not familiar with endianess, you can give that a Google. What is it? Okay, so what is endianess? It's essentially what side of the bytes, where should the computer start reading from for binary data or hexadecimal data. Let's see if we can find a nice chart. Let's see, let's look for a different website or just go to images. Let's see, this might be good representation. Okay, so little endianness and big endianness represented with two sides of the egg. We see here the little side, the smaller side of the egg is being cracked. Then alternatively on this other side, the bigger end of the egg is being cracked. Why are these eggs? This is just in reference to the book, the novel Gulliver's Travels, where the two inhabitants, the two tribes, faculties, whatever they were, groups, were having a war, a dispute over which side of the egg to crack. Should we crack from the little end or should we crack from the big end? And computer scientists kind of pulled from that. And now we have two different ways that binary data is read. So if we have the integer 0a, 0b, 0c, 0d, right here, these hex values, where should we start reading? Should we read from here at 0a or should we start reading here from 0d? And you see in little endian, we do start on this right-hand side, and then we go to the left. So it would be 0D, CBA, alternatively, in big endian, we do ABCD. Very confusing, kind of annoying, and it's a weird problem, especially when you get into any type of like network programming, and you need to use functions like H2N, so H2NS, host to network order and network to host order. It gets pretty annoying. It gets pretty annoying rather quickly, but let's exit out of all of this and let's actually download that challenge binary that we talked about from before. So make dir endianness. I'm going to enter into a bash shell just because. Download this file. Is that correct? Is that what I wanted? I downloaded the source code. Let me launch this instance. There we go. We get this netcat thing to connect to, this netcat connection line. Smash the enter key. Make sure you guys can read that. Welcome to Endian CTF. You need to find both the little endian and the big endian representations of a word. If you get both correct, you will receive the flag. And then it gives us this word, SUZRB. So just completely random garbage. So enter the little endian representation of this. So there's a few ways we can do this. We can once again go back to CyberChef, our favorite website for capture the flag challenges. We don't want that. We do endianess. Raw. What was it? Can I just grab this? That looks pretty ugly. Probably need to convert this to hex. To hex. Delimiter, none. So that's one way. That's one path we could do. Alternatively, we can use a command line tool called RAX2, which is from the Radare package, the Radare project, and Radare 2 just being a very powerful tool for reverse engineering. It's a command line tool very similar to GDB or IDA. And bundled with it, you have other utilities, one of them being RAX2, which is a command line expression and like binary converter thing. So this command allows you to convert values between positive and negative integer, float, octal, binary, and hexadecimal values. So how can we do this? We see this flag here, tac E to swap the endian values. That might come in handy. And we see these other strings. We see attack little s can convert from a hex string to a character. So if we feed it hex, it'll print out the characters, the English like letters. Alternatively, if we do a capital S, it will convert from a hex string or from characters to a hex string. So let's see if we can give that a shot. RAX2, attack big S, and then slam in our text. And we do get this output. We do get this hexadecimal. If we wanted to be sure whether or not that is actually the correct representation, hit the up arrow. We see it starts with 7.3 for S. If we do RAX2 and then tac A, it will actually print out an ASCII table where everything is ordered nicely in octal and decimal and hex and character. So if we go down to hex 7.3, which is actually on this side, hex 7.3, we do get the character S. And if you don't have RAX installed and you still want to look at an ASCII table, you can just run the man ASCII command and you will still get access to the ASCII table in your terminal. So that's pretty neat. If you ever have a need to quickly look for ASCII tables and for whatever reason you don't have access to the web browser or the internet, you can just do man ASCII or RAX2 tac A. So coming here, if we smash the enter key, we do get that this is incorrect, denoting that this is actually in big endian format. We want it in little endian format. So we can come here and we can add in a tac E and give that a shot. However, it doesn't actually swap the endianness. So that is kind of lame. It is kind of annoying, if I do say so myself. If I add a space here, it will print all of these on a new line, and it does become a little bit easier to like visualize on how we need to piece these back together. So we just need to put these essentially in the reverse order for little endian. Seven 5 7 3, hit enter, and then that is correct. And now we know that this original value, this output was the big endian. So we can slam that in and we solved it correctly. We entered the big and little endianness and we get our flag. Pico CTF, endian swap success. Sweet. You can grab that, come over here and slam it in. Oh, and then in CyberChef, we can take out this check mark for pad incomplete words, and we do see that it created the same results. Actually, it didn't. That's interesting. That's something I had to play around with a bit more. I'm not sure why it's in this order, but there you have it. Pretty neat, nifty ways. When I have the chance, I do like to use command lines tools over web tools or anything else, just because it's fun. So that's it. We'll wrap it up on that challenge. This video is getting a bit long. Hopefully it was valuable. Hopefully you guys learned some stuff, right? Binary addition and binary operations. You typically never have to do them from hand like this. So unless you're doing a homework assignment, you never really need to break out a truth table. But it is good fundamental knowledge to know, because you never know when you might need it for some type of reverse engineering task. You might not see or and that often, but a very common one is XOR, right? Exclusive OR. That's a very common function that is used, but more on that later. So as always, guys, let me know in the comments below if you found a better or a different way to solve any of these challenges. Let me know what kind of videos you want to see. Take it easy, and see you guys in the next video.